Hi Flashes, today we are going to be talking about probability and reviewing the things that we talked about within probability. So the first thing that we talked about was likelihood of events. So if you guys remember, we talked about the probability number line. And remember, probability is always a number that is between 0 and 1. So when you have a probability of 0, that means that something is impossible. When you have a probability of 1, that means that it is certain. So it is certain that it's going to happen. Okay. Then in between, so in between 0 and 1 is 1/2. At 1/2, we say that this is equally likely. So for example, if we have 4 yellow jelly beans and 4 red jelly beans in a bag, the probability of getting a yellow or red is the same because it's 4 and 4, so they're equally likely that you'll get one or the other. And then in between these, so in between 0 and 1/2, we say it's unlikely that it's going to happen, but it could still be possible. So unlikely. And then in between 1/2 and 1, we say that it is likely. Okay, so looking at the different options here, let's figure out what each one of them is. So rolling an even number on a number cube. So thinking of all of our numbers on our number cube, we have 1, 2, 3, 4, 5, and 6. And notice all of our even numbers are 2, 4, and 6. So there's 3 out of 6 numbers that are even numbers on a number cube. And if I were to reduce that, that would be reduced to 1/2. So the likelihood of rolling an even number, the probability of 1/2, is what we say equally likely. Okay, next one, rolling a 5 on a number cube. So rolling a number 5, there's only one number 5 on a number cube out of 6 numbers total. So the probability of rolling a 5 is 1/6. So looking at my probability line, 1/6 is going to fall right in between 0 and 1/2. So we say that it is unlikely that it's going to happen. Next one, rolling a number greater than 2 on a number cube. So numbers greater than 2 are 3, 4, 5, and 6. So that means we have 4 out of 6 numbers on a number cube. The probability of getting a number greater than 2 is 4 out of 6, which is equivalent to 2/3. So thinking of our probability number line, 2/3 is going to fall in between 1/2 and 1. So that is going to be likely that that will occur. And then the last one, rolling a number less than 1 on a number cube. Well, there's no numbers less than 1 on a number cube, so that is going to be impossible. Okay, so again, whenever you are talking about the likelihood of events, you want to remember this probability number line like we talked about in class. Okay. All right, complementary events are 2 events. When added together, they must equal 1. Okay, so 2 events when added together, they must equal 1, which is the same thing as like 100% or 1/1 as a fraction, so it must be equivalent to 1. Okay, so if one event is 0.64, 0.64 plus what is going to get us to that 1? Well, to figure out this missing piece, all that you're doing is you're taking 1 minus 0.64. So 1 minus 0.64 is 0.36. So the probability of event B is going to be 0.36 if probability of A was 0.64, because again, add those together, that will equal 1. If we have probability of 3/7, so again 3/7 plus what is going to give us that 1. So let's say 3 out of 7 candies were yellow in the bag how many of them would be anything other than yellow? Well, if 3 out of 7 were yellow, that means that 4 out of 7 would be anything else, because 4 plus 3 gives you that 7 out of 7, which is equivalent to 1. So probability of B would be 4/7. And then probability of A, 22%. So again, we're trying to figure out 22% plus what is going to be equal to. In this case, it's not going to be 1. It's going to be that 100%. So just take 100% minus 22, and that will give us 78. So again, when you get done, if you were to add your probability of event A and your probability of event B, it should equal your probability of 1. And when you're talking about percent, you're talking about 100%. Okay, so let's find basic theoretical probabilities. So the first portion here is using a number cube, and they want us to write it as a fraction, a decimal, and a percent. So on a number cube, what would be the probability of getting the number 4? Well, there's only one number 4 on a number cube out of 6 numbers total, so the probability of getting a 4 is 1 out of 6. Because again, only one number 4 is on the cube out of 6 numbers total. So there's our fraction form. So now we need to change it to a decimal. So if you guys remember to change fractions to decimals, all that we do is divide. So 1/6, or 1 divided by 6 is 0.16 repeating. And then to change a decimal into a percent, you just move it 2 places to the right. So if I were to add on another number 6 here to help us out, if I move it 2 places to the right here, this would be equivalent to 16.6, or if you guys want to round it to like 16.7, that is completely fine too. Okay, so prime probability of getting a prime number. So if you guys remember, a prime number is any number that can only be divisible by 1 in itself. So only 1 times that number gives you that number. So let's think of all of the numbers on the number cube, and let's figure out how many of them are prime. So if you guys remember, 1 is neither a prime or a composite number. So you do not want to include the number 1 with a prime number. Now look at number 2. So number 2, can only 1 times 2 give you 2, or is there other multiples that can give us 2? Only 1 times 2 gives us 2, so 2 is a prime number. What about 3? 3 is also a prime number because only 1 times 3 is 3. What about 4? 4 is not a prime number because 1 times 4 is 4, but you can also take 2 times 2 to give you 4. So 4 is not a prime number. 5? It is, because only 1 times 5 is 5. And then 6 is not, because only 1 times 6 is 6, but you can also do 2 times 3. So probability of getting a prime number, how many numbers did we circle? 1, 2, 3, out of 6 numbers total. So the probability of getting a prime number is 3 out of 6, which reduces to 1/2. Okay, so let's change this into a decimal. So again, to change a fraction to a decimal, you are just dividing. Numerator divided by denominator. So 1 divided by 2 is 0.5. To change a decimal into a percent, you're just moving that decimal point 2 times to the right, and you see an empty spot here, so you're just going to fill it in with a 0. So 0.5 as a percent is 50%. And then the last one here, a number less than 3 on a number cube. So a number less than 3, you do not include 3. And we need all the numbers to the left of it. So we have 1 and 2, so those numbers are less than 3. So the probability of getting a number less than 3, we have 2 numbers out of 6 numbers total that's less than 3. So 2 out of 6 is equivalent to 1/3. 1/3 as a decimal, so I'm dividing, is 0.3 repeating. And when you're changing this decimal to a percent, if it's repeating, okay, we can go ahead and write some 3's down here. Again, you're just moving it 2 places to the right, and then let's just round it to the nearest tenths. So 0.3 repeating as a percent is 33.3%. Alright, so now moving on to the spinner down here. So what would be the probability of getting a vowel? So if you guys remember, your vowels are A, E, I, O, and U. So we need to count how many vowels are on the spinner. So I see 1, 2, and 3. So I see an O and 2 E's. So the probability of getting a vowel is 3 out of, and then we need to count how many letters are there total. So 1, 2, 3, 4, 5, 6, 7, 8. So 3 out of 8 is the probability of getting a vowel. And again, change it to a decimal, you just divide. So 3 divided by 8 is 0.375. And then to change a decimal into a percent, you just move that decimal point 2 times to the right. So 0.375 as a percent is 37.5%. Alright, next one is getting the probability of an N. So probability of getting N, we need to count all the N's on the spinner. So I see 1 and 2. So there's 2 out of 8 letters total that are N's. So probability of getting an N is 2 out of 8, or in other words, 1/4. And then again, just change it to a decimal and a percent. So 1 divided by 4 is 0.25. 0.25 as a percent is 25%. Alright, and then the last one here, probability of getting not an A. So we need to count all letters that are not A, and if you guys notice, it's actually all of them. So there's 8 out of 8 that are not A, which is equivalent to 1. 1 as a decimal is just still 1, because if you were to take 8 divided by 8, that gives you the 1/1, or your decimal will still just be 1. And then to change this to a percent, remember that 1 is represented as what we set up here, which is 100%. Because technically there's like an imaginary decimal point at the end of any whole number, and when you move it to the right 2 times, you have 2 empty spaces. So that is why you would get that 100%. So when you spin the spinner, we are certain that you are not going to get an A because there's no A's on the spinner. Moving on to the next page. So they say to make a tree diagram for flipping a coin and then rolling a die and then give it sample space. So if you guys remember, a tree diagram is talking about the outcomes that you get from these events. So the outcome of flipping a coin, you get heads or tails. So I'm going to put H or T for heads or tails. And then the outcome for rolling a die, you can get a 1, 2, 3, 4, 5, or 6. So whenever you create your tree diagram, you start with whatever event is first. So the first event is flipping a coin, and then you list the outcomes. So the outcomes when you flip a coin, you can get heads or you can get tails. Then your second event is going to tell you how many branches you need depending on how many outcomes there are. So if we are rolling a die, we know that there are 6 outcomes. So we need 6 branches going off of each of your heads and tails. So 1, 2, 3, 4, 5, and 6. And you're just going to label them with your outcomes of rolling a die. So 1, 2, 3, 4, 5, 6. And same thing down here. 1, 2, 3, 4, 5, and 6. So there's your tree. So this is telling us all of our different outcomes that we can have. So to figure out how many outcomes there are, you just count your last total branches. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 different outcomes, okay? So we are going to use our tree to help us with the sample space. So the sample space is that you are listing all outcomes possible. And you're just looking at your 12 outcomes and working backwards to the beginning of the tree. So the first branch here is saying that the coin can land on heads and you can roll a number 1. So the first sample space is a heads 1, so H1. Your next one could be an H and then a 2, so heads and then roll a number 2. Or you can get an H3, H4, H5, or an H6. So this sample space is representing the top part of our tree. You can flip a coin and it lands on heads, and then you can roll a die and you can get a 1, 2, 3, 4, 5, or 6. Okay? But then let's say the coin doesn't land on heads, let's say it lands on tails. So you're going to do the same thing over here for your second part of the sample space. So your coin can land on tails and you can roll the die and it lands on a 1, or it can land on a 2, or it can land on a 3, 4, 5, or 6. So when you guys notice, when you get done, if we said that there was 12 outcomes up here, you should make sure you have all 12 outcomes possible in your sample space. Okay, so let's try another example. So make a tree diagram for the following event. You are going on vacation and want to pack 3 shorts, 2 pairs of shorts, or 3 shirts, 2 pairs of shorts, and 2 pairs of shoes. How many different combinations do you have? So again, in your tree diagram, you are starting with the first event. So the first thing that we are choosing, or the outcomes that we are choosing, are the shirts. And if we have 3 different shirts, I'm going to label them as shirt 1, shirt 2, and shirt 3. Okay, so that's the first part of our tree. Next part is the second event. So now we are going to pick between 2 pairs of shorts. So since we only have 2 pairs of shorts, I'm going to have 2 branches going off of each of my shirts. And I'm going to label them as short 1, short 2, and then same thing with all the branches, short 1, short 2, short 1, short 2. So again, the first part of your tree is your first event of what you're choosing from, or the outcomes. The second part of the tree is going to be how many branches for the second outcomes. So we have 2 different pairs of shorts, so we have 2 branches to represent short 1 and short 2. And then we still have another event, which is choosing the pairs of shoes. So we have 2 pairs of shoes. So off of each of these, I need to have 2 more branches for shoe 1 and shoe 2. So your branches are going off of each of the outcomes before them in the tree. Okay, and then again, you're just labeling them: shoe 1, shoe 2, shoe 1, shoe 2, shoe 1, shoe 2. So that when you guys get done, your tree should look something like this. So you have your 3 shirts, and then you had 2 branches going off for each pair of shorts, and then 2 more branches going off for each pair of shoes. So when you get done, to figure out how many different combinations you have, you just count your last column. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So we have 12 different outcomes possible for outfits. So your sample space, again, you're just listing all of your different outcomes possible. So you just start with your tree. So you start with outcome number 1. and you just work your way back to figure out what outcome number 1 was talking about. So outcome number 1 was talking about shirt 1, short 1, shoe 1. So shirt 1, short 1, and shoe 1. Option number 2, if you go back, was shirt 1, short 1, and shoe 2. Option number 3, so work your way back, was shirt 1, short 2, shoe 1. And then your 4th option was shirt 1, short 2, shoe 2. And that took care of the first part of the tree. So was shirt 1. Okay, but let's say you don't pick shirt 1 and you pick shirt 2. So the pattern that's going to happen is all of these, the shirt or the short and the shoes, are going to stay the same, but instead of shirt 1 being all the ones, you're now just going to have them as shirt 2. So your option 5 is shirt 2, short 1, shoe 1. So the same as this, but change that to a 2. So shirt 2, short 1, and shoe 1. Option 6, shirt 2, short 1, shoe 2. Option 7, shirt 2, short 2, shoe 1. And option 8, shirt 2, short 2, shoe 2. And that takes care of the second shirt. Okay, so again, notice how these were the same for both. All that we did was we just changed the shirt number. And then we still have one more shirt left, so shirt 3. And again, it's going to stay the same. So shirt 3, short 1, shoe 1. Shirt 3, short 1, shoe 2. Shirt 3, short 2, shoe 1, or shirt 3, short 2, and shoe 2. So again, when you get done, if we set up here that we had 12 different outcomes, if I were to count my sample space, I have listed all the different possibilities. So if you need to pause the video, please do so at this time, because I'm moving on to the next page. Alright, so the counting principle says that to figure out how many outcomes are possible within certain events, all that you're doing is you are multiplying all of your different possibilities together, and that will give you how many outcomes possible. So first one, if you roll a pair of dice, how many outcomes are possible? Well, if you roll the dice the first time, you can get a 1, 2, 3, 4, 5, or 6. So you have 6 different possibilities when you roll the first die. Then when you roll the second die, again, you have 6 different numbers that could pop up. So counting principle says you can just multiply both of those numbers together. So 6 times 6 will give you 36 different outcomes. And number 16, a company puts a code on each different product they sell. The code is made up of 3 numbers and 2 letters. How many different codes are possible? So when you're thinking of numbers, so think of the numbers on like your computer. You have the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So these are your numbers that make up any number that we need. So if we need 3 sets of numbers, so 1, 2, 3, we need to figure out how many numbers can we choose from for each one of these numbers. Well, 0 through 9, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 different numbers we can choose from for the first number. times 10 different numbers we can choose for the second number times 10 different numbers we can choose for the last number. Okay, but then we also have 2 letters. So 2 letters, well, think of how many letters we can choose from in the alphabet. There are 26 different letters we can choose. So for the first letter, I have 26 different letters I can choose from. And then for the second letter, I also have 26 different letters I can choose from. So counting principle says I can just multiply these numbers to figure out all the different combinations possible. And we get 676,000. Okay, next one, you have 4 different keys and 5 different marbles. How many outcomes are possible? Well, if you have 4 different keys to choose from, that is your first number. And then if you have 5 different marbles to choose from, that's your second. So just multiply those together, and that will give you 20 different outcomes. And the last one, so this one is similar to number 16. You choose 5 digits and 2 letters for a passcode. How many outcomes are possible? So if I'm choosing 5 digits, so 1, 2, 3, 4, 5, so those make up the digits. And then 2 letters for a passcode. I need to figure out how many different combinations are there. So again, when we're thinking of digits, we're thinking of numbers on our computer. And how many different digits were there? There were 10. So for my first digit, I have 10 different possibilities I can choose from. For my second digit, I have 10 I can choose from. My third, fourth, and fifth, once again, I have 10 different digits I can choose from. So I'm just going to multiply all those together. And then for letters, so if my last 2 things in my passcode are letters, how many different letters can I choose from? I can choose from 26 different letters. So 26 different letters I can choose for my first one, and then the same for the second. So to figure out all those outcomes, just multiply those numbers together. So 10 times 10 times 10 times 10 times 10 times 26 times 26. And we get 67,600,000. So 67,600,000. All right, moving on to prediction. So when you are predicting, you are going to set up a proportion, because you will be either given 3 numbers and you have to find a missing number, or you have to first find the probability of what was given to you, and then you have to set up a proportion to figure out your prediction. Okay, so the first one, Caitlin finds the experimental probability of her making a 3-point shot is 30%. Out of 500 3-point shots, about how many could she predict she would make? So this one you could actually do just one step to get to your answer. You could just take 30% of 500 and that will give you your answer. Or, like I said, we can set up a proportion. So you always start with the experimental probability or the theoretical probability. So if they said that her experimental probability was 30%, think of percents are always out of what? Percents are always out of 100. So that would be my first fraction in my proportion. And then if I'm trying to figure out how many out of 500 would we predict she would make, 500 is a total, so I need that number in my denominator, and then I need to solve for x. So if you guys remember to solve a proportion, you just cross multiply. So 100 times x is 100x. 500 times 30 is 15,000. And then your last step to get x by itself is to divide by that 100 on both sides. So out of 500 shots, we would expect her to make 150 of them. And then same thing with number 20. If you roll a number cube 15 times, about how many times do you expect to roll a number less than 6? So we need to know, what is the probability of rolling a number less than 6? What's its theoretical probability? So the theoretical probability of rolling a number less than 6 is a 1, 2, 3, 4, or 5. So that's 5 numbers out of 6 total that are less than 6. And then again, we are trying to figure out, if we were to do it 15 times, how many out of those 15 times would we expect it to also be a number less than 6? Okay, so cross multiply. 6 times x is 6x. 5 times 15 is 75. Divide both these numbers by 6, and 75 divided by 6 is about 12.5. So since we are predicting, we'll just round it up to the nearest whole number, so we'll say 13. All right, use the spinner below to answer the following questions. So in 20 spins, about how often can you expect to get a number that has a factor of 6? So if you guys remember, factors are numbers that can be multiplied together to get that number. So factors of 6, looking at the spinner, I have 1 and 6 because 1 times 6 is 6. And I also have 2 and 3 because 2 times 3 is also 6. So altogether, I have 1, 2, 3, 4 numbers out of 6 total. That would be a factor of 6. So that's your first fraction, because again, we're still predicting. And then if we were to spin this 20 times, we need to predict how many out of those 20 times would we also expect to get a factor of 6. Okay? So cross multiply. 6 times x is 6x. 4 times 20 is 80. And then divide both sides by 6. So 80 divided by 6. Again, we're just going to round to the nearest whole number, and that would give us another 13. All right, and then the last one, so in 150 spins, about how often can you expect to get a number less than 6? So less than 6, we have a 5, 4, 3, 2, and 1. So that's 5 numbers out of 6 total that are less than 6. So that is our theoretical probability that we'll start with. And then we are trying to predict how many times out of 150. Okay, so again, cross multiply. 6 times x is 6x. 5 times 150 is 750. And then divide both sides by 6. So 750 divided by 6 is 125. Moving on to our last page. So a number cube is rolled 50 times, and the results are shown in the graph below. If you guys remember, when we talked about theoretical and experimental probability, theoretical probability is what's supposed to happen. So when you do something one time, so theoretically it's supposed to happen. Experimental is when you do something more than one time. Okay, so that is when we would be doing like our predictions. Okay, so 23 says, what's the experimental probability of rolling of 5? So experimental is coming from this table because they rolled a die 50 times. So that is experimental probabilities because they did it more than once. So the experimental probability of rolling of 5, check out to see how many 5s did they roll. So here is their number that they rolled, and they did it 5 times. So they rolled the number 5 out of 50 times. And I do want to reduce here, so 5 goes into both 5 and 50. So 5 divided by 5 is 1, and 50 divided by 5 is 10. So the experimental probability of rolling a 5 was 1/10. What is the theoretical probability of rolling a 5? So theoretical is when you just do it one time. So if I roll a die one time, how many 5s are on a number cube? 1 out of 6 number total. So the probability of rolling a 5 was 1/6. And then if I were to compare these, okay, so like compare the experimental probability to its theoretical probability, I could just change these to decimals by dividing. So 1/10 is equivalent to 0.1, and 1/6 is equivalent to 0.16 repeating. So if I were to compare these, the theoretical probability of 0.16 repeating was greater than the experimental probability, which was 0.1. Okay, so when you're comparing, you're using your inequality symbols to help you compare. All right, and then the last two here. So what is the experimental probability of not rolling a 1? So not rolling a 1, we need to add up how many times did they not roll a 1. So they rolled a number 2 8 times, a number 3 6 times, number 4 9 times, number 5 5 times, and number 6 12 times. So 8 plus 6 plus 9 plus 5 plus 12 is 40. So they rolled not a 1 40 times out of 50 times total. So 40 out of 50 reduces to 4 out of 5. And then theoretically, what's supposed to happen when you do not roll a 1? So how many not 1s are on a number cube? 5 out of 6 total. Okay, so the theoretical probability of not rolling a 1 is 5 out of 6. And again, if I wanted to compare, I can just change them to decimals. So 4 divided by 5 is 0.8. 5 divided by 6 is 0.83 repeating. So once again, the theoretical probability was greater than its experimental. All right, so that is it. So that is everything that we learned in this probability unit. So let your teacher know if you guys have any questions.